Hey guys, welcome back to my channel. This is the second try of shooting the day 37 video. It's the extension of backtracking from yesterday. So we're still exploring the recursive backtracking, but with a further constraint. But on a bigger scale, the general template is the same that we're going to use. So yesterday when we were doing the cocoa eating monkey, we had the template which specified the base case and then also the recursive case, which would continuously call the backtracking function um, to to explore the path until it exceeds the target. So right before it exceeds the target, it will stop. So yeah, let's go straight into the question. It's Leetcode 39. I'm going to share my screen with you guys. Yes, finally it's working. So, the question is, given an array of distinct integer candidates and a target integer target, return a list of all unique combinations of candidates where the chosen numbers sum to target. You may return the combinations in any order. The same number may be chosen from candidates an unlimited number of times. Two combinations are unique if the frequency of at least one of the chosen numbers is different. Okay, um, so we cannot have um, two combinations that's not unique, right? So that would be like 2, 2, 3 and 2, 3, 2. So the numbers inside the array is the same, but then their combination is different. In this case, it's not unique, so we cannot use the combination. So it's different from permutation, right? That we explored last time. So we have to keep that in mind. So basically the problem is asking, given a target and candidates, from this given array, we have to find combinations in which could make up to this target, which is 7. So that includes 2, 2, 3. So this would add up to 7, and then 7, which itself would add up to 7. So we have these two combinations. So how would we show this in a backtracking tree? So given there's a root node, and then let's say that we have 2, 3, 6, 7. So 2, 3, 6, and 7. So from here, the sum of the path, all the elements in the path is 2. The target, let's say we have to make 7, right? Now, from 2, we have 4 options, right? Because it said the same number may be chosen from candidates an unlimited number of times. So this can also have a 2 as its child node. You can also have 3, 6, and 7. So there's 4 children nodes. And if you add up 2 and 2, it becomes 4. This becomes 5, 8, and 9. And when you see that it exceeds the target, which is 7, you know that we can abandon this leaf. This is also called in term called pruning. So you're just abandoning this leaf and then not further exploring. So that's also the point of backtracking, right? So we stay in this leaf and then explore further. So this would have another 4 possibilities. And then we do the same way. If it exceeds the target, then we abandon it. If it doesn't, we just keep it. 4 nodes. So we do the same for all of these 4 nodes that connects to the root node. And then later at the end, we're gonna specify which combinations, so which paths. So for instance, 2, 2, 3 would make up 7, right? Which path would specifically fit our target constraint, which is 7. So yeah, in this case, there will be two possibilities, 2 to 3 and 7 itself. So the backtracking algorithm will correctly specify that. So how are we going to code this? So we need to find combinations that sum up to target. So, and to keep this target track of the current sum, we, like yesterday, we need to first specify the helper function, the backtracking function that we're going to use as a recursion. And there should be a current. So that's an integer variable that's passed to keep track of the current sum, right? Current sum of the path. We also need an argument path to represent the numbers in the current path. So this is what current did in the last problem, right? When in Coco Monkey. So we need path variable to represent the number, current variable to keep track of the current sum. What else? We also need, no, that's about it that we need from this. And then we also need to build the base case first, right? So when the base case current equals target, so current sum equals to target, then that means the base case will be a leaf node, and that would already fit the target. So we stop the function from running then. So in this case, we would specify the base case first. But before that, let's finish this helper function, the base backtracking function. So there should be a path. There should be a start, the index in the candidates list where the current iteration begins, because we don't have to start from the beginning, right? This ensures that the combinations do not repeatedly repeat the previously considered elements. So this is what makes it unique, like said in the description, where 2 combinations are unique if the frequency of at least one of the chosen numbers is different. So we have to specify this start and then also the current to keep track of the sum. And now sum in the path. So now if now we build a base case. So base case would be if current equals to target. So if the current already meets its target, then we're gonna append to our answer list. This will be the empty list that we're gonna fill it up as we go. Answer dot append, and we append the copy of the current, right? So we make the copy, and then we end it here because we have already found the target. Now, we build the recursive backtracking iteration. So for I in range, let's not forget the answer equals empty list. Start and length of the candidates. So the loop iterates over candidates list. So we can see that That's why we did length of the candidates here, starting from the index start. And like we stated in the beginning. So this avoids considering the repeated, the same element before the current path. So it ensures the uniqueness in the backtracking. We also did this yesterday. And if no, num equals candidates I, if current plus num is less than target. So what I did here is I first select the um, current candidate number. So for I, and if the current sum plus the current number that we add from the path, if it doesn't exceed the target, that means that we can move further into the path, right? So we're gonna add path.append num. We can add the number, and here we recursively call the backtrack function to explore further with the updated path and sum. So that would be backtrack path. So we're going to explore it with the current I, the updated path, and the sum, right? So that will be current plus num, because that's the new sum. And then after the recursive call returns, then the last number is removed from the path. So like yesterday, we pop it. Now we have the empty list here. And we just have to start the backtracking process, and that will be done by backtrack 0. 0 starting index is 0, and then current sum is 0. So yeah, then finally return the answer. Let's see if this works. Invalid syntax. Answer append path. Because we're appending the copy of the path, right? Start is not defined. I have start here. Start current. List path target to return. This is out of the index, right? So this should be here. This should be inside this backtracking function. So it was out of the scope. So that's why it wasn't working. Hopefully this works. Yes. So guys, yeah, that was it for the recursive backtracking example. It was a simple example, and it was also the one that I struggled also, but it is not that hard if you know the backtracking template by heart, and then you just keep on remembering when to add path and when to add sum, and also specifying the constraint when it exceeds or when you meet the target. And yeah, anyways, thank you guys all for listening, and like always, if you guys have any comments, let me down below. I always listen. I always check the comments. And some were really memorable. So please, if you have anything to say, share it with me. Or else, yeah. Okay. See you guys tomorrow. Maybe we're gonna continue with dynamic programming, or if we have something left from this backtracking, we're gonna explore that.